celebration of the ITC, I recalled that when I was in my 20s, it was actually the subject of the first ITC luncheon I ever spoke at. Happily enough, the resolution is quite poor at the bottom right, so you can make your own decisions as to whether I was one of the people who didn't age at all or aged quite poorly, as Afi said. So what I wanted to talk about today is maybe starting from, this is a good place to start, this picture here, which is one of the fundamental standard predictions that n-body simulations have been able to make, and it really is one of the triumphs of the model of structure formation through hierarchical clustering. And this is an image which shows the dark matter halo of the Milky Way predicted by the Aquarius simulations. And what you notice is that the halo of the Milky Way, or halo of galaxies like our own, is surrounded by this vast sea of structures of smaller and smaller halos of dark matter that surround it, that could themselves be potential hosts of galaxies. And this is essentially one of the fundamental predictions that we get, that we have lots of small objects surrounding somewhat bigger objects. So this is a fundamental prediction. And a second fundamental prediction comes around with regards to the distribution of material within these halos. And to recall a famous saying, there's only three certainties in life: death, taxes, and that simulations predict NFW profiles, right? And so this is essentially this realization that has come around as a result of high-resolution simulations of dark matter halos, which is that if you were to take the density as a function of radius from the center of a dark matter halo, irrespective of whether you're looking at a galaxy cluster or you're looking at a dwarf galaxy, if you sort of rescale them in some appropriate units, they all seem to show a very similar kind of structure, where the central part of the profile has a slope that goes as 1 over r, the middle part goes as 1 over r squared, and the outskirts goes as 1 over r cubed. And so this is what we call the NFW profile. And so a question you might ask is this universal structure something that is predicted universally all the way down? You might ask, well, what does all the way down mean? And this actually relates back to a question that came up in Anna's talk, which is, what are the smallest structures that we expect to form in the universe? And the answer to that question depends on what we think the dark matter is. So here's a really nice visualization by Jens Stucker, which shows essentially the initial power spectrum of structures in the universe. We have wave number on the x-axis, large scales on the left, small scales on the right. The y-axis is the so-called dimensionless power spectrum. So it's just the power spectrum multiplied by k cubed. And essentially what you have is that if you imagine the universe is made up of purely cold dark matter, it's completely cold and collisionless, you get this dashed yellow line, which is sort of hidden beneath the other curves, where you have increasing power in smaller and smaller scales, which is why we have small structures forming first, bigger objects forming later. That's the hierarchical structure formation model. However, if you have a variation to your dark matter model, say warm dark matter, where the particle can be of the order of a few keV, that basically results in free streaming of the dark matter from small-scale perturbations, and it actually cuts off the power spectrum at a particular scale defined by the particle physics of the dark matter. And that scale occurs roughly at the scale of dwarf galaxies, which is why looking at substructures in the Milky Way becomes a very powerful test of warm dark matter. However, even in the cold dark matter paradigm, there is such a cutoff, depending on what you think the production mechanism is. In the standard neutralino case of 100 GeV or so, this cutoff is at many orders of magnitude smaller than dwarf galaxies, around the mass scale of the Earth. And so if you were to sort of make a very simple visualization of what the spectrum of things we expect to form in a cold dark matter universe is, it spans something of the order of 22 orders of magnitude or so. And the things that I've been talking about, the fact that we can predict the abundances of objects in detail, the fact that we know that they have these universal density profiles and so on, are things that have really essentially been established at these scales of the very tiniest dwarf galaxies, or at least the objects that should host the smallest galaxies themselves. But there's this whole range here where we don't necessarily know what their structures actually should be at the present day. And this is kind of what I mean by, is the universality present all the way down to the very small scale structures in this universe. So there have been attempts to answer this question, but there have been some limitations with this, as you can imagine, because you're trying to resolve extremely tiny things, much smaller than what you would even consider the highest resolution simulation particles that have ever been run in n-body simulations, right? So what people do to work around this problem, or have done in the past, is to say, okay, well, since we're only interested in the tiniest objects, we don't need a massive gargantuan simulation to answer that question. So we'll take a very tiny region of the universe, so it's only a couple of kiloparsecs in size, so this is work done by Raul Angulo and collaborators. And then you run the simulation forward, but you have to stop this at very high redshift. So you can't run a simulation so small up to the present day. And the reason being that at a certain point in time, the characteristic nonlinear scale of the universe actually becomes comparable to the size of this box. So your assumptions on large-scale perturbations actually breaks down, so you can't run this further forward. So you have to analyze the density structure of halos at these early redshifts. And this is what people have done, and what they find is rather interesting, which is actually that you do find universal density profiles, but they're universal in a very different sense. They're not really NFWs anymore. So here are 6 examples of density profiles from these simulations. The different colors show the structure measured at different redshifts, all at very high redshift. And what you notice is that they kind of follow these single power laws. So it's no longer -1, -2, -3. But for a fairly large range of radii, at least at the very highest redshifts, it's a single power law with a slope that is comparable to -1.5 or so. And interestingly enough, this feature, these density profiles, seem to form almost immediately as the initial peaks themselves are collapsing. So it's not something that is building up very gradually over time. And so this type of density structure has been referred to as a prompt cusp. Okay, so it's forming promptly following collapse, and it's just a single power law cusp. So that's the situation at the scale of these Earth-mass dark matter halos, at least at the very early times. But what is the picture at present day? So is this something that we actually expect to see at redshift 0 as well, at the epoch that we live in? So when I was here in the ITC, this is a program that we began. And like I said, this is a very challenging thing to do because you need to resolve very, very small things. And in order to get them resolved at the present day, you need a cosmologically representative volume. So this is work that I actually did in collaboration with Volker as well. And the idea behind this is what is essentially called the zoom technique, where you start with a big simulation like this. So this is around 7. This is actually a version of the Millennium simulation in some sense. So it's a normal cosmological volume. The characteristic mass of halos is of the order of 10 to the 14 solar masses. You then pick a region of interest. And what you do is you degrade the resolution everywhere else outside that region of interest and focus all your computational power on that little circle. And so then what you get is a smaller region, now resolved at higher resolution, still embedded in the same large-scale structure. Now you see that the characteristic mass scale has gone down by 2 orders of magnitude. Find another region of interest, resimulate that. Find another region of interest, resimulate that. And you continue this over and over and over and over again until you get to this point here, which is 9 levels of simulation down, where we now have a region, a high-resolution region of a size 25 parsecs embedded in an 800 megaparsec volume. So this really is a testament to the amazing power of supercomputers nowadays and algorithms these days. And I think it's a project that almost broke Volker at some point. But we eventually did get to this point where you're resolving the smallest halos in the world, in the universe, rather. And you notice that the cosmic structure in this scale is very different to what we saw in the image of the Aquarius simulation. It's not now a sea of dark matter halos floating all around, but it's a lot of smooth dark matter structure with just the smallest halos resolved, which have the characteristic mass of around 10 to the minus 6. To give you a sense of the numbers involved in this, the first 3 levels of simulation in this actually capture a particle mass of around 1,000 solar masses, which for a long time has been the best simulations that have ever been done. When you get to our level 8, an individual dark matter particle has a mass of 10 to the minus 11 solar masses. It's around the mass of the atmosphere of the Earth, okay? And so what that allows you to do is you can now actually stitch all of these volumes together and build up what is the complete halo mass function of the cold dark matter universe. So basically, it's the number of dark matter halos as a function of mass normalized by the volume. So the first 3 levels of simulations are shown here. These are the different lines. And when you add all these volumes together, you now span 22 orders of magnitude, all resolved in the same cosmological volume. And it actually shows a remarkable level of similarity, at least in abundance. What do the structures themselves look like? Is there universality after all? This is basically now taking all of the characteristic halo masses in these different levels, shown in the different colors. This is now again showing a density profile, but shown slightly differently. It's actually showing the slope as a function of radius. And you notice that the dotted and dashed lines are essentially predictions of the NFW model and a variation of that, a more generalized version of that called the INASTO profile. And actually all the curves showing masses all the way from cluster scales down to the Earth masses followed the predictions of the NFW pretty well, okay? So, I mean, there is a bit of variation around it, but in general, it seems that at the present day, even the most extreme mass scales are well described by the universal form. So clearly, there is some contradiction between what we're finding at present day versus what the simulations seem to be suggesting at the time of initial collapse. So we can try and understand this better. So what's actually how do we bridge that gap? And a good place to start, I think, is to see what the theory should tell us to expect. And the ideas of objects collapsing from some initial peak reminds us at least of the ideas of self-similarity and spherical collapse. And actually inspired by Avi's comment earlier today, I tried to see what artificial intelligence can tell us in terms of giving us a picture of what it thinks self-similar collapse of mass shells should look like. And this is what it came up with. Maybe not the most useful analogy to draw with respect to what I want to show, but where artificial intelligence fails, a former ITC postdoc really comes to your rescue. So this is a visualization by Benedict Diemer, which basically shows the idea that if you have a spherical, unfortunately the contrast doesn't show very well, but if you have a first spherical perturbation in the early universe, which is collapsing under gravity, you can think of the collapse of these different mass shells essentially as rescaled versions of one another that collapse in the same way over time. And as objects initially fall under the first collapse and then go back to their second apocenters and so on, they start building up these shells of matter that creates a density structure. And you can actually calculate, when you work through the equations of this model, what you think the density profile should look like as a function of radius when something is collapsing from an initial peak that is surrounded by a smooth background density, like it should be in the case of these Earth mass first dark matter halos. This is work that was done by Simon White in 2022, and you find a radial dependence of density that goes as -12/7, which is kind of like -1.5, actually, as those simulations seem to suggest. So how do we go from that prediction of the -12/7 to an NFW-like form? So this is essentially a project that has been done by a phenomenally talented student of mine in Durham, Yu-Chan Wang. And to try and address this question, what she's been doing is to essentially take the same dark matter halo, okay, where the dark matter halo, the characteristic scale at which it forms is shown by the vertical dashed line. So there's different objects that are simulated here. And what we do is we essentially take that same object and change the level of the initial fluctuations by artificially truncating the initial power spectrum at different scales. We just cut it off by hand. So what that means is that for the same object, we're able to see what is the effect of moving it either closer to or further away from the cutoff in the initial power spectrum. So this is what it looks like. So here are 3 images of what basically this region where this dark matter halo is collapsing out of looks like at some early time. It's at redshift 7.8 or so. On the furthest left, we have the situation where the cutoff is on the largest scale, so we smooth out over a lot more structure. On the right-hand side, we have the cutoff on the smallest scale, so we allow more structures to form. So The left can be thought of as being closer to the scenario of the Earth mass halos. The right can be thought of as closer to the scenario of kind of what we see like for the Milky Way in some sense. And you notice at the same time, they look quite different from one another. The object on the furthest left really hasn't collapsed at all. It's still showing the initial Lagrangian patch, which it will eventually collapse from. Whereas the object on the right, by this time, has already started showing features of shell crossing, showing features of filaments, and the formation of an initial dark matter halo actually beginning. If we actually now run this simulation forward and see what it looks like, for the cases where the cutoff is on much smaller scales, you see the typical feature of filaments basically collapsing, dark matter halos coming down these filaments, objects merging, building up structures, and so on. And because this is still a low-mass object, it's not going to be filled with low-mass structures surrounding it, but you still see other smaller things orbiting the main halo. On the other hand, if we look at something that is really close to this cutoff, you see that as time is progressing, you don't really see much else happening beyond just the formation of the primordial filament from which it's growing. And essentially, once this filament collapses, this object forms in one go, almost monolithically. And this is essentially the conditions under which these prompt cusps are forming. And essentially, there's very few other objects around that this thing could possibly merge with. So if you want to understand where the density profile of a dark matter halo actually is constructed from, you can actually look at where its particles originate. Okay, so this is a slightly complex diagram, so I'll just explain this to you in a second. So what's happening here is going from left to right, I'm showing the simulation of the same dark matter halo with slightly different initial conditions, where the power spectrum has been moved to smaller and smaller scales until it's cut off. And the different colors essentially take the particles that belong to the dark matter halo at some late time in the universe, and then color-coded by whether they belong to the main halo, so i.e. they're collapsing from the main peak, or whether they are particles brought in by other objects, things that this halo then eventually merges with. It then takes all of those particles back to the initial conditions and puts them on a diagram of linear density versus the Lagrangian position, and it creates this envelope. So why do we do this? It's because putting them on a diagram like this actually allows us to study which are the particles we think might follow more closely the self-similar collapse model versus which are the particles that we think should be most perturbed away from that, which should not be collapsing under the assumption of self-similarity. And the way you can do this is essentially because you can actually fit a polynomial that allows you to separate these particles out pretty clearly. But as you can see, when the cutoff is moved to really, really small scales, you have many more colored points beyond cyan because you have many more small-scale structures that are formed. And so here's what happens. This is a dark matter. This is now 3 time sequences shown from top to bottom, with the particles in the halo at a particular redshift, which is marked by the label on the bottom left, shown on the furthest left column, that linear density figure on the middle column, and the right now shows the density profile multiplied by r to the power of 12/7. So that means if things are prompt cusps that have that slope, they will appear flat on this profile. And what I've done here is change the colors so that all the particles that we deem to be collapsing under the self-similarity condition are marked in red, whereas everything else that builds up the density profile eventually is shown in white. And what you notice is that as this thing is initially collapsing, the self-similar component is kind of flat, follows this 12/7 solution, and that it remains true to later times, whereas the outer parts of the halo, which are being made up by objects that eventually accrete onto this halo and build the density profile, are the ones that deviate away from the self-similarity condition. And in fact, the shape that it creates is a shape reminiscent of an NFW profile. So the NFW profile is being gradually built up by the material accreted onto this primordial cusp that collapsed out of the peak. And this turns out to be rather a universal feature. Whether you look at the example of a merger, so an NFW in these units looks like that shape. Again, I'm showing the self-similar component in the solid lines on the upper panel, which is down, again, the density multiplied by r to the 12/7, and all other components shown in the dotted lines, you always see that this prompt cusp-like feature is preserved, and the NFW is essentially built up over time as a result of further accretion. This happens not just with mergers, it happens when you have interactions with filaments and so on. And so essentially, a generalized picture you can build is the following, that when a dark matter halo collapses out of an initial peak, there are two things that could happen. It could look like a prompt cusp, it could look like an FW or whatever, but typically what we find pretty generally is that the density profiles of structures collapsing right near the free streaming scale of dark matter appear as prompt cusps initially. There can be many things that happen over the course of their lifetimes, all these kinds of interactions and mergers and so on. And what that does is that it causes a gradual transition away from this prompt cusp solution into something that looks more and more like an FW, but the prompt cusp can still remain right at the very center. So the very centers of dark matter halos, much below the scale of what we typically resolve in simulations, actually are much steeper than what the NFW solution might actually be. So I think that actually then gives us a picture of where NFW profiles come from. Why do dark matter halos look universal? It's because they actually follow these two stages of growth and evolution that is pretty universal, regardless of what you do with cosmology, your power spectrum, where things are growing, what mass scale they have, and so on. And ultimately, everything is tied to the later evolution of objects, what is happening to these objects over the course of their lifetimes after their initial collapse. And so clearly there's something about how dark matter halos grow through time that tells us about why they should have this characteristic shape. And actually this link between the assembly history of dark matter halos and their final structures is something we've known for a long time. So this is an example of some work I did with Aaron Ludlow a few years ago. And what it shows here is, just focus on, say, CDM in this case. There's different dark matter halo masses shown with the different colors. It's funny units on these axes, where on the y-axis we have mass scaled by a characteristic mass. We have density scaled by a characteristic density. There's two types of curves, one which shows the median density profile of objects, one which shows the average accretion history of dark matter halos. And they both look exactly like NFW profiles in rescaled units. And in fact, you can predict one from the other just through a simple scaling. And this is actually the reason why we can predict things like the concentrations of dark matter halos directly from their assembly histories. It's because in rescaled units, they look identical to one another. And there's little dependence on all other features. So I think I have about 2 minutes left. Let me tell you why any of this is important, okay? One, I think, is because it's kind of interesting, theoretically speaking. It's a fundamental question related to structure formation. But I think there's also a reason it's interesting from the perspective of dark matter annihilation, because we expect that if dark matter annihilates as Majorana particles and so on, we expect that the flux from annihilation should be some combination of features to do with the dark matter model itself, but more importantly, from a cosmological perspective, what the density of the dark matter is along the line of sight, so specifically the density squared, okay? And this is, of course, what the dark matter halos themselves are contributing. In the Aquarius simulations, there was a very nice demonstration of this fact, which is what if you were to break down the annihilation contribution that we might see in the Milky Way from what is just the smooth component of the dark matter halo on the top left versus what we get from small substructures floating around in the Milky Way on the top right, and the unresolved components that we get basically from the fact that we have many more subhalos than we're actually able to resolve in the simulation. And what you find is that actually the annihilation luminosity might be dominated by really low mass objects because they're much more abundant, and they could be really quite dense as well. An example is shown in this figure here, which shows what the annihilation luminosity is as a function of radius. And essentially the idea is that depending on what we think the lowest mass dark matter halos are that still survive in the Milky Way, the flux boost we expect to annihilation from the smallest structures could be a factor of 2 greater than what we get from the smooth component of the Milky Way itself. And so the main takeaway is that if there are lots of these prompt cusps that still survive in the Milky Way today, which have much denser central slopes than what the NFW profile actually predicts, there could be a significant modification to what we actually expect the annihilation signal to be from dark matter, particularly in the outer halo. So here are my concluding thoughts. So the universality of halo profiles are actually kind of twofold in some level. You get these prompt cusps that form and stabilize immediately after peak collapse, which then transition to an NFW-like shape later on. These tend to converge towards NFW regardless of what you kind of do. I mean, sometimes these prompt cusps do survive, but it's not always the case that they remain completely like that. And the reason why this sort of very universal eventual history takes place is because the assembly of dark matter halos themselves are universal and show a shape reminiscent of the NFW itself. And the prompt cusps may be preserved right at the very centers of dark matter halos, and this can actually have important consequences for dark matter detection, for example, through annihilation radiation. Okay, so that's where I'll stop. Thank you.
So, taking at face value what you showed us, if you look now, as you know, there are the ultra faint galaxies that seem to have more of a core-like distribution. So, if you assume that there's no nucleus, and if you assume that gas and stars follow the dark matter, then would you conclude that that these type of ultra faint galaxies had some interesting assembly history? If I understood correctly, they have the prompt thing because it's a little bit more foreign than NFW, so they didn't treat other things. That's the conclusion that you can draw from your result.
So there's a few aspects in the answer to that question. So actually the prompt cusps here that you would expect form on really very tiny scales. So this would be smaller than what we think the typical core sizes of these ultra-faint dwarfs are. So for example, in a cold dark matter setting, the size of these prompt cusps are a couple of parsecs in size. Okay, so these are really quite far in. Now, in terms of what happens with regards to whether cores form or not, I think the connection with the assembly histories is something that people have been considering for quite a while now. In fact, there are these ideas that there's actually correlations between whether you identify an ultrafaint dwarf as having a core depending on whether it had recent star formation or not, for instance, because these cusps are always very good at reassembling. So you need something to essentially keep that core going once it's already been created to prevent the cusp from forming again. But the prompt cusps themselves will be formed on really tiny scales, at least if you think the dark matter is a cold dark matter particle. If it's a warm dark matter particle, then the prompt cusps are actually a little bit bigger. And in fact, there's some work by Stendelos that shows that because of the size of the prompt cusps that are predicted by these models, because they can be on somewhat hundreds of parsecs of scales, there are actually constraints from local group kinematics that might rule out certain classes of warm dark matter models.
So there is another interesting context that you can apply these calculations, and that's in the context of elliptical galaxies that follow collisionless mergers. But now we can see the collisionless particles, it's the stars. And actually 20 years ago we made an analogy between NFW and the profiles of elliptical galaxies with Jim Peebles. Can you look into that in terms of those galaxies that are red and dead, not making any new stars and just following mergers, perhaps the ones in the centers of clusters?
I suppose at some level, because they are ultimately collisionless particles, as you say, you can follow that same analogy. There will be a fundamental limit, of course, where they start deviating when you hit the phase space limit of the dark matter because of Liouville's theorem.
It's the stars.
But here it's the stars, yeah. So there will be some point at which they start diverging. But I think, there has been, for example, if you look at the papers by Fillmore and Goldreich and so on from 1984, there are basically applications of the same idea of how peaks are collapsing and stuff to things like things collapsing onto black holes and so on as well, right?
It would be interesting to see the brightness profiles of ellipticals. If you can explain them, that would be nice.
keep that for ITC at 30, I think. Thanks.
What about if you extrapolate your results to the very low mass subhalos? Let's say even to the Earth size,
Mm-hmm.
do they be still around the stochastic?
Yeah, no, I think that's an interesting question for sure. So I think there's a couple of things one needs to think about when it comes to predicting, for example, what the population of these objects is at the present day. One is what do the tides of the galaxy, what does the potential of the Milky Way essentially do in terms of stripping these objects and whether they will completely destroy them? That actually turns out to be, not such a big problem. So these are quite resistant to those effects. The other question is how many of them will survive near the center of the Milky Way versus what survives on the outskirts. And actually there's a calculation by Delos and White which looks at how these objects might get disrupted through encounters with stars, because actually the tidal forces from stars can be large enough to destroy these prompt cusps. So actually when it comes to predicting what the boost to the annihilation radiation is that you get from these really tiny objects in the galactic halo, you get a much stronger boost in the outer halo than you get in the inner halo because of that region, because the stellar density becomes a lot higher. Mm-hmm. Oh, like quite possibly they would have been, yeah. I don't know the answer to that definitively without doing the calculation. So that's actually something we are attempting to do at the moment. The issue with the numerical calculation here is that you need to follow the evolution of these really tiny objects, but still have the appropriate potential of the Milky Way for this. There are ways around that problem to bridge that dynamic range, and that's actually a calculation that a few of us are working on.
More questions? If not, let's thank Sownak again.